Okay, now to do gradient descent, we need to be able to compute basically the derivative of the in-sample error with respect to a change in the weights. So if you imagine that you have the weight in layer WL going from the previous node I to the layer L node J, okay, so then the derivative of the in-sample error with respect to this weight is approximately equal to, almost by definition, is approximately equal to the in-sample error, for the weights WL, IJ, plus some tolerance H minus the in-sample error, okay, for the weights WL, IJ minus some tolerance divided by twice the tolerance. Okay, so this is the finite difference approximation to the derivative, to the gradient. Okay, and so we need to compute this. We need to compute for all weights. Okay, so this is size of the number of weights. Okay, the size of all the weight matrices added up together. So we need to compute this for all the weights. Okay, and so let's see how long it's going to take us to compute. Well, we need to compute so what does this notation mean? This notation means that I'm computing the in-sample error by perturbing these weights up H, leaving all other weights the same, and perturbing the weights down H, leaving all other weights the same. I compute the change, the sensitivity of the in-sample error, okay, the change divided by H. Okay. So I need to compute this, and this is what's sometimes called the numerical derivative. Okay. And it's an approximation, and you can get it more and more accurate by choosing H very, very small. H approximately 0.0001 will give you a pretty accurate estimate of the gradient. 0.0001. Okay. The error in the estimation is order of H squared. So you can do the Taylor analysis to see that the error is order of H squared. Okay. But you have to compute this for all the weights. You have to compute the derivative to get the gradient. The gradient is the derivative, is the vector of derivatives with respect to all the weights. So you have to compute this derivative with respect to all the weights. So that's W computations. And each of these is taking basically NW. Okay. So this in-sample error, okay, is going to take running time to compute of order of NW, okay, plus NV times W. Where I've kept these separate because this is theta computations and this is multiplication. So, but basically NW squared. And nowadays people want to use neural networks with a million parameters. Okay, and to use a million parameters, you better have a lot of data to train it. So N is going to be also order of a million or more. Okay, so you've got a million squared. That's 10 to the 12 times a million. That's 10 to the 18. Okay, that's 10 to the 18 just to compute one gradient. Okay, and now you have to do gradient descent, so you have to compute the gradient many times. Okay. So, the numerical derivative is a very simple way to compute the gradient. Okay, and whenever you compute the gradient, so you can, if you analytically compute the gradient, you can always use the numerical derivative to check your analytical computation, but it's not a very efficient way to get the gradient. Okay, and we would be done with neural networks if we didn't have a more efficient way. Not to mention the fact that it is approximate. Okay, so now I'm going to come back and show you a very efficient way to compute the gradient. Okay. Essentially, we can compute the gradient in the same running time that it takes us to compute the in-sample error. Okay, so it's almost as efficient as just computing the in-sample error. Here you see computing a single gradient, a single derivative is as efficient as computing the in-sample error. We're going to show that computing all these derivatives is as efficient as computing the in-sample error. So we can remove this W. Okay. And it's a dynamic programming algorithm that allows us to compute all the gradients. Okay. It's a little bit sophisticated. So, the first time you see it, you're not going to understand it. The second time you see it, you're not going to understand it. When you come to implement it, that's when you will understand it. Okay. And so we'll go through this famous algorithm. It's a dynamic programming algorithm that allows us to compute all these derivatives in one shot. Okay. Getting rid of this factor of W. Okay. And that algorithm is called backpropagation. So let's erase and come back and talk about this algorithm, backpropagation. It's essentially an algorithm that allows us to get the gradient in an efficient way. Okay, it allows us to get the gradient in an efficient way, and then we just use it in the gradient descent algorithm, okay, to fit the neural network to the data. to implement gradient descent, we need to compute the derivatives with respect to the weights. So we need, the derivative of the error, okay, and we do it point by point with respect to the weights WL. Okay. Now, let me mention that this is a matrix of weights going into layer L. So this is a matrix of derivatives, one for each weight. So this is a matrix of derivatives. Okay, and what are the dimensions of this matrix? Okay, so this matrix is 1 plus dl minus 1 by dl. So it implements this weight matrix has dl perceptrons, and each of those perceptrons is computed on the previous layer's output, which has dimension 1 plus dl minus 1. Okay, so we need the derivatives of this form, of these matrices of derivatives. In particular, we need every matrix of derivatives because we need to do gradient descent. So we need to compute the gradient with respect to every weight, i.e. all the weight matrices. Okay, so what we're going to do is derive this, famous algorithm called backpropagation. Okay, and this is essentially dynamic programming. Okay, that computes all these matrices of derivatives in one swoop. Okay, and that's what makes it efficient. Now, okay, it's going to be intense. There's going to be a lot of algebra, a lot of calculus, lots of chain rule, and so on and so forth. So, when you might have to, you might not, get it on the first go. You might not get it on the second reading. Okay, and you'll read the text carefully, and you'll follow the notes, and you'll follow the lecture. You'll only really get it when you implement it for the assignment. And then after that, many of you who go on to just use neural networks, will download a package and use it. But if you want to do research, or if you want to manipulate, or if you want to make things faster, and so on and so forth, then you need to know the nuts and bolts. If you want to tailor the neural network, for example, if you want to change the activation function or something like that. Okay, so we need to compute this matrix of derivatives, okay, and it's going to be useful to have in your mind the picture of what's going on in layer L. So if you have layer L, there's an input SL, okay, then you have your transform theta, okay, and that computes the output XL, okay, and this output, okay, now how did we get this input? So you have your previous layer, which was sending, XL minus 1, okay, and you have your weight matrix, and this is where the weight matrix WL comes in. Okay, it multiplies these weights, the weight matrix multiplies the output, okay, and so you're computing a bunch of perceptrons as the input signal, okay, then you transform, you get the output signal, and then, you'll have another weight matrix here, WL plus 1 to compute, the signal SL plus 1, and so on. Okay, so that's the picture of what's going on when we're running the neural network to compute the output. Okay, and so we want to get the matrix of derivatives of the error with respect to each weight in this layer. So let's see if we can compute at least the derivative with respect to one of the perceptron weights. So, going into node I, so if this is node I, okay, in this layer L, okay, so there'll be a perceptron, there'll be the perceptron that's implemented by WLI. Okay, so that's a column in this weight matrix, one of those perceptrons. So let's see if we can get the derivative of the error with respect to that column of weights. Okay, so dE, derivative of E with respect to the column of weights, a single perceptron in this layer, DLI. Okay. Now, the interesting thing is that this single perceptron only affects the output through node I's input. Okay. So by the chain rule, this is equal to the impact that a change in these weights has on that signal going into node I. So the derivative of the signal going into node I with respect to the weights, okay, times the derivative, the change. So this is how much the signal changes times, the derivative of the error with respect to the signal. Okay, so times how much the signal affects the error. So the change in the signal times the change in the error due to the signal. This is the chain rule. Heuristically, you can think of these two deltas. So if you approximated this with deltas, this is a change in the weight, change in the signal, change in the signal, change in the error. These two deltas, in some sense, cancel. Okay, and you get change in the error divided by the change in the weight. So this is the chain rule. Okay, and now let's see if we can compute this guy. Okay. So this guy here, so what is the signal? SLI is equal to W Li transpose XL minus 1. Okay, so this is the linear signal. Okay, and we're trying to compute the derivative of the signal with respect to the weights. So the derivative is just going to be the coefficient. Now you can sit down and check this. You're going to or take it from me that the derivative of the signal with respect to the weights is just equal to the coefficient XL minus 1. Okay, and this is, these are the weights. This is a column of weights, so this has dimension 1 plus DL minus 1, and so does this, so at least the dimensions agree, and you can work this out for yourself or take it from me. Okay, so I'll erase this, okay, and we've just computed that this guy is XL minus 1, so this is equal to XL minus 1 times dE by dSLI. Okay, good. Okay. But this is just, one column of derivatives in this matrix. So this derivative, the matrix of derivatives, I'm going to have to do this for each column. So I'm going to get XL minus 1 times derivative of E with respect to SL1. Okay, that's one column. Then the next column will be XL minus 1, dE by dSL2, and so on, XL minus 1, dE by dSL, dL. Okay, I have dL columns. Okay, but now I can just factor out the XL minus 1. So this here is equal to XL minus 1 times a row vector, which is the derivative of the error with respect to the first signal, derivative of the error with respect to the second signal, derivative of the error with respect to the dLth signal. Okay, so that's just XL minus 1, okay, times this, so this is a column vector, times this row vector, which is dE by dSL. Okay, so now this is a vector of derivatives, but I have to take the row version of this transpose. Okay, so what have I deduced? That the derivative of the error with respect to a particular weight matrix in layer L, okay, that matrix of derivatives is given by the output of the previous layer times a vector of derivatives with respect to the incoming signals, okay, transpose. Okay, and you can check the dimensions of this and the dimension of this, and everything matches. Okay, fantastic. So let me erase this. Okay, and let us define this guy as the sensitivity with respect to the inputs to layer L. Okay, we'll call this delta L. Okay, and so this is XL minus 1 delta L transpose. Okay, the sensitivity with respect to SL, the input to layer L. Okay, so there, I have gotten an expression for this matrix of derivatives in terms of two. So this is a matrix of derivatives, and it's in terms of whatever the output is of layer L minus 1, and we'll have to deal with that later. What is that? Okay, but whatever it is, okay, so that's an important point, that you can only define the sensitivities, okay, once you know what the input is. Okay, so let us assume for the moment that we have an input. Okay, so the sensitivity of the error is the error on some input. So let us assume that we have an input, and we've done the forward propagation, and we've computed all the outputs. Okay. So then this derivative, now if you change the weights, you will change the output, the error. You will change the error by an amount that is the output from layer L minus 1. Okay, and a derivative of the error with respect to the inputs to layer L. Okay, so we're going to call this delta L. Okay, the sensitivity for layer L. Okay. Now this we can easily compute for my input X. So let's see if we can compute this sensitivity, because otherwise it doesn't look like I've gained anything. I've taken one derivative and put it in terms of another derivative. Okay, and this picture is going to be useful again. Okay. So we want to compute the derivative of the error with respect to the sensitivity L. So we want to compute the derivative of the error with respect to the sensitivity SL. Okay. Okay, so this derivative of the error, this sensitivity, this derivative of the error with respect to the signal into layer L is a vector of derivatives. Let's see if we can compute one of its components. Okay, so derivative of the error with respect to SL, let's say I, is equal to now that SLI, the input to node I, only affects the output, the error, through how it affects the output of that node, XLI. So by the chain rule, this is the derivative of the error with respect to XLI times the derivative of XLI with respect to SLI. But XLI is just theta of SLI. So this derivative is just theta prime, the derivative of this transform, okay, theta prime evaluated at SLI. Okay. So this is equal to theta prime of SLI times the derivative of E with respect to XLI. Okay. And so that's one of the components in here. Now this is a vector of derivatives, so I need to just collect all these guys up for different I and put them in a vector. So I will write that as, so I get all these components, so theta prime evaluated at all these values, so theta prime of SL. So now this is a vector, and I'm doing component-wise multiplication with respect to this vector of derivatives. So the derivative of the error with respect to the vector, output vector XL, okay? Except that I only need dimensions 1 to DL. I don't need to consider the augmented one because there's no product in here for the augmented one. This is only for, I going from 1 to DL. Okay? So I get, and I'll use the notation O times to indicate, component-wise multiplication of the vector of derivatives dE by dXL. Okay, so let me erase this and write this a little bigger. Okay, so this is dE by dXL. So let's see what this is. So it's saying that, I want the sensitivity, okay, for the input with respect to the input into layer L. It's the derivative of the transform function evaluated on that input, component-wise multiplication with the derivative, the vector of derivatives of the error with respect to the output of that node. And here I only need components 1 to DL. Okay. So let's see if I can compute this guy now. Wow. Okay. So many times we're going to use the chain rule. And that's why I said this is an intense algebraic derivation. So the derivative of E with respect to XL, okay, is equal to, so now let's see. So how does the output depend on XL? Well, it depends on XL through how XL affects each of the inputs to the next layer. Okay, so by the chain rule, now this is the chain rule. There are many inputs here, so I have to sum over the effects that X has on all of these inputs together with the sensitivity of the error with respect to those inputs. So this is the sum over K equals 1, the sum over K equals 1 to D L plus 1. Okay, so those are the number of inputs here. The derivative of the error with respect to each of those inputs, S L plus 1 K, multiplied by the derivative of that input with respect to XL. With respect to XL. Okay. But again, we know that SL plus 1K, so SL plus 1, the kth node in the L plus 1th layer, is equal to W L plus 1K transpose XL, which can equally well be written XL transpose WL plus 1K. So the derivative, so this is now, I want to take the derivative, so this is a linear signal. It also depends linearly on X as well as on W. So I want to take the derivative of this linear signal with respect to X. So the derivative of SL plus 1K with respect to XL, okay, is equal to WL plus 1K. Okay. Okay, so here I end up with, this is equal to the sum from k equals 1 to d, L plus 1, W, L plus 1, k. This is the kth column of W, L plus 1. Okay, that's this term times dE by ds L plus 1 k. When I weight the columns of a matrix by certain coefficients and add, so this is a weighted sum of the columns of W. Okay, so this is just WL plus 1, and you can do the linear algebra, the matrix multiplication to show that. This is WL plus 1 k times the vector dE by ds L plus 1. dE by ds L plus 1. Okay, and by definition, this is just the sensitivity in layer L plus 1. So this is equal to WL plus 1, the sensitivity in layer L plus 1. Okay, so let me erase this and summarize. So this is equal to theta prime of SL O times, which is component by component multiplication for vectors. Okay, WL plus 1, the sensitivity, and so this is the sensitivity in layer L. Sensitivity in layer L is equal to, some expression, okay, WL plus 1 times delta L plus 1. Okay, and I need the components 1 to DL, 1 to DL. And so I haven't really doesn't look like I've gotten anywhere, because all I've done is I said I need this sensitivity in order to compute this matrix of derivatives. Okay, and what I have done is I've analyzed, and gotten an expression for this sensitivity and this sophisticated complex expression. Okay, but it turns out that this is progress, because I've gotten this expression, I've gotten this sensitivity in terms of an expression that involves the sensitivity in the next layer. Okay, so this is so conclusion. Let me erase all the derivation. Conclusion. Sensitivity in layer L, i.e. delta L, is related to the sensitivity in layer L plus 1, i.e. delta L plus 1. Okay. So let's continue that logic. The sensitivity in layer L plus 1 will be related to L plus 2. L plus 2 will be related to L plus 3. L plus 3 will be related to L plus 4, and so on up to the final layer delta L. Okay. And so if I can compute the sensitivity in the final layer delta L, so if I can compute delta L, okay, then this equation tells me what delta L minus 1 is. Okay, and I can iterate and get delta L minus 2. And I can iterate and I can get delta L minus 3. In fact, I can keep going all the way up to delta 1. Okay. And in this way, I can compute all the sensitivities delta. Delta 1, delta 2, delta 3, all the way up to delta L, but I have to start at delta L. Okay. So, we've done all this algebra, and at the end of the day, that's the basic conclusion. Okay. That I can compute sensitivities in any layer L by starting at big L and going backwards. Okay. And why do I care? Because the sensitivity in layer L multiplied by the output of layer L minus 1 gives me my matrix of derivatives with respect to the weights WL. Okay. And that's why I care. So let me summarize that. Let me summarize these equations now, and we will come back and develop the backpropagation algorithm for computing the gradients, and then the full algorithm for using gradient descent on the data, and then we'll look at some results. So now we can summarize. Okay. So we want to get this matrix of derivatives. It's equal to xl minus 1 times delta L transpose. And we don't know what this delta L transpose is. We know we can compute the outputs. Okay, we can even compute the signals. Okay, so what is this delta L transpose? Delta L transpose, delta L is equal to theta prime of SL, so the derivative of your transform evaluated at the input to that layer. Okay, now we're going to do element-wise, component-wise multiplication of two vectors, okay, of the weight matrix into layer L plus 1, okay, times delta L plus 1, okay, and we have, we only need components 1 to DL. This is a DL dimensional component by component vector multiplication. That's why I use O times to indicate that. Okay. So let's erase this. And I'll tell you now how we're going to compute all these gradients. Okay, so we're done with the meat, the hard part of the derivation of the backpropagation algorithm. Now, if you're like me, if you're anything like me, you're not going to believe something until you see the derivation or the proof. And in general, I think that's a healthy attitude, to have always seek the derivation, seek the proof. But at the end of the day, we also want to be practical and we need to implement neural networks. And so what do you need to know at the end of the day? At the end of the day, it's these two equations that are golden. Okay, this is more or less what you need to know to just implement the neural network. And then if you need to sort of change things, okay, then you need to get into the nuts and bolts. Okay, so the gradient of the error with respect to the weight matrices, with respect to the weight matrix in layer L is given by this expression, the output of layer L minus 1 times the sensitivity for layer L, and this is a matrix product, okay, and so it has to have the correct dimensions. And we have this, you can think of it as a recursion, okay, but it's like a forward recursion. So we have this forward recursion for the sensitivity in layer L as an expression involving the sensitivity in layer L plus 1. Okay, now let's see how we can use these two equations together with what we know to do gradient descent to minimize the in-sample error. Okay. And what I'm going to describe is stochastic gradient descent. So you pick a random data point. So you're at you've got a architecture, you've got a configuration for your neural network, which means you've set the weights, you've set each of the weight matrices. Okay. And now you pick a random data point. So stochastic gradient descent. Okay. So you pick a random data point xn. Okay. And now you can compute the output and the error that we're currently making on this xn. So you run forward propagation. Okay, so what does this do? This sets xn equal to the outputs of layer 0. Okay, and there's an augmented one here, so everything is fine. And then, we're using the weight matrix, W1, you compute S1, and then so this is W1, and then using the transform, you transform the signal into layer 1, into the output of layer 1, okay, and then you continue, you compute S2, and then the output X2, and so on, until you get to SL, and then the output XL, and then that is H of Xn, and then you can compute E of H of Xn and Yn. Okay. And that's so reasonably straightforward. We know how to do the forward propagation. Okay, so that's the first step. Okay, is we can run the forward propagation, and we know how long that takes. Okay, the next step is run back propagation, and that's going to involve these two fundamental equations. Okay, and the idea here is to compute all the gradients. Okay, so run back propagation. Okay, i.e. compute all gradients. Okay, and then let me show you what that entails. In backpropagation, we now need to compute all the gradients, all the matrices of gradients with respect to each matrix of weights WL. Okay, now In order to do that, we need the outputs at each layer, and we need the delta L's for each layer, okay? And in the forward step, you see we've computed all the outputs for each layer, okay? So we've got half of what we need in order to compute the gradients. And now let's see how we compute the other half, okay? And we're going to start by computing delta for the final output layer. So delta L. We start with delta L. Okay, and so now let me remind you what delta L is. Okay, delta L is equal to the derivative of the error with respect to what? With respect to SL. Okay, and now we can do this computation with any error. I'm gonna work with the squared error. So E is equal to XL minus YN squared. So the output minus yn. So, you know, when you have a data point, pick a random data point xn, yn. Okay, so E is the squared error. So then this derivative, dE by dsL, is equal to the derivative of xl minus yn squared with respect to SL. Okay, which is equal to twice xl minus yn. Okay, times the derivative of xl with respect to SL. And we've done this calculation before, so I'm just doing it quickly, which is twice XL minus YN times the derivative of XL with respect to SL, which is theta prime of SL. Now, okay, in the interesting case where we choose the tan H for all of our activation nodes, and this applies here as well as here, the tan H is particularly convenient because the derivative of tan H is 1 minus tan H squared. So this is 1 minus tan H squared of SL. Okay, but tan H of SL is just XL, so this is 1 minus XL squared. So at the end of the day, we get for the squared error and the tan H activation function, we get twice XL minus YN, 1 minus XL, that quantity squared. Okay, and so this, you know, last step is for the tan H activation function. And, you know, this step is for the squared error, but you could implement this entire chain for any error you choose as long as it's differentiable, and for any activation function you choose as long as it's differentiable. Okay, so we have computed delta L. Okay, so this is equal to twice XL minus YN, 1 minus XL, that quantity squared. Okay, we have computed delta L, at which point we can spit out the gradient with respect to the Lth layer weights. So at which point we can spit out dE by dW big L is equal to XL minus 1, okay, which we have. Okay, we've computed all the x's, so XL minus 1 times delta L. Okay, we can spit out that gradient. Okay, good. So let me erase this little derivation and illustrate pictorially what's going on. So for the final layer, you know, we have computed, so layer L, we have computed delta L. And I'm going to illustrate it going backwards. Okay, so we have computed delta L. And you'll see why I have illustrated going backwards, because we're going to start with delta L and then move backwards. Okay, so now we need to compute delta L minus 1. How do we compute delta L minus 1? Well, this is where this equation becomes so handy. Okay, we just take theta prime of S L minus 1. So theta prime of S L minus 1. Okay, O times W L, okay, delta L plus 1, which is, in this case, delta L. Okay, but here we only need 1 up to D L minus 1. So it's a little bit cramped, okay, but essentially I'm implementing this formula, okay, in order to compute delta L minus 1 from delta L. So this gives me delta L minus 1. Okay. And why do I know I can do this? Well, because in the forward step, I have computed the input to layer L minus 1. Okay. In the forward step, I computed the input to layer L minus 1. Okay. And the weights are certainly known. And I have just computed delta L. Okay. So this step is well defined, and the moment I compute delta L minus 1, boom, I can spit out dE by dW L minus 1, the weights going into the L minus 1, which is just equal to x L minus 2 times delta L minus 1. Oh, sorry, I forgot the transpose. Okay, so now look, I've computed two sets of gradients. Okay, let me show you pictorially what's going on. Pictorially, look at what happened. I have my delta L. I multiplied by the weights WL. So I have my WL. Okay, WL. Okay, so I got the result. Multiplied by the weights WL, got the result. Okay, and then for each, component-wise, I multiplied the result of each component by the corresponding component of this vector, which is theta prime of SL minus 1. So I multiply by theta prime of SL minus 1. Okay, and then that gives me delta L minus 1. Look at that beautiful picture. Okay, to show you what's going on here. Let me just do one more step. Okay, one more step is I can get delta L minus 2. How do I get that? It's theta prime of S L minus 2 O times W L minus 1 times delta L minus 1. But I only need the components 1 to D L minus 2. Okay, and at the moment I calculate delta L minus 2, I can spit out dE by dW L minus 2, which is equal to x L minus 3 times delta of L minus 2 transpose. Okay, and let me show you pictorially what's going on here. You take my delta L minus 1, you multiply by the weight matrix WL minus 1. Okay, take my delta L minus 1, multiply by the weight matrix WL minus 1. Now I'll send it into each node, so that gives me the signal going into each node, multiply by theta prime of SL minus 1. Okay, and then out pops delta L minus 2. Wow, beautiful. Okay, and in this way I can compute delta L minus 3, spit out dE by dW L minus 3. Okay, using the same formula. Okay, and so on, all the way to delta 1, and spit out dE by dW1, which is equal to x0. What is x0? x0 is just the input features times delta 1 transpose. Okay, and if I continue this, okay, up until delta 1, okay, that's the pictorial illustration of this process. Beautiful. And in this process, look what's happened. I've spit out all the gradients of the weights, all the gradients of the error on this data point with respect to each weight matrix. Okay? And this pictorial is quite intuitive and quite nice for visualizing what's going on. Essentially, we are running the neural network in backwards. Okay? When we did forward propagation, we initialized with x. Okay, the features xn, and then we propagated forward and got x1, x2, x3, x4, x5 up to xl. Okay, and in backward propagation, we're running the network essentially backwards. We initialize with delta L, okay, and then we run it through the weights. Okay, it's a different kind of transform, but it's a transform. We run it through the weights, transform, run it through the weights, transform, run it through the weights, transform, and so on all the way back. So we're running the network in reverse. Fantastic. Okay, and in the process, we ran one forward propagation, okay, and one backward propagation to compute all the deltas, okay. And you see that this backward propagation to compute all the deltas is, again, just like the forward propagation. It's going to touch all the weights once, and it's going to go through each node once, except that here we're computing a derivative of the activation function. So when you pick your transform function, it's important that the transform function is itself efficient for the forward propagation, and the derivative is also efficient for the backward propagation. Okay, but essentially the same runtime for backward propagation, and spitting out the matrix of derivatives is just one matrix multiplication, which is exactly the size of the output. okay, which is the number of weights. So very efficient runtime, essentially equivalent to 2 or 3 forward propagations. The third one comes from the fact that you have to do these matrix multiplication. And we get the gradient of the error with respect to all the weight matrices. And now in the SGD framework, what do? We update each weight matrix. WL gets updated to WL minus eta times the gradient of this error with respect to its weight matrix. And so you pick a random point, run a forward, run a backward, get all the gradients, update all the weights. Pick a data point randomly, run a forward, run a backward, get all the gradients, do an update. Boom, 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 boom. That's stochastic gradient descent. Wonderful. Now, if instead of stochastic gradient descent, you wanted to do the batch version, the full gradient descent, well, in that case, you need to first, for each data point, do the forward and backward and compute the gradients and then store the sum of these gradients, because the gradient of the sum of these errors is the sum of the gradients. So you store the sum of the gradients and then do one update once you've processed all data points once. Okay. And we already saw the pros and cons between the batch version versus the stochastic gradient version. It turns out that the SGD version is what is popular in practice today for 2 reasons. 1, we saw the efficiencies, and 2, because it's much easier to distribute on parallel architectures, especially when your data is distributed. Wow, fantastic. Bam, 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 bam. Okay, so now we have the mechanism for minimizing the in-sample error to choose the weights that optimize minimize the in-sample error. And so that's what it means to fit the neural network to data. So let me show you what happens when we do it on the digits data. Why not?